Hello. This week we will talk about the exponential functions. And to be more exact, we will talk about the calculus of exponential functions. First of all, let's double check if we remember the shape of the exponential functions. The formula is a to the x. Domain of the exponential functions are all of the numbers. Base of the exponential number is always positive and, however, is never 1. Which means the middle part is not really the graph of exponential function. We have base less than 1 and base greater than 1. That's the shape. We know, we're confident, we remember. We also have general pictures. Okay. All of the increasing functions are the exponential function with the base greater than 1, and all of the decreasing are functions with the base less than 1, decreasing, of course. This one, I still put this one on the graph, but as we know, it's not really an exponential function. It's just a constant function, which is a little bit too easy. Okay, now let's look at some behavior of the exponential function, which in calculus way, we will talk about the limits. Since the domain of exponential function are the interval from negative infinity to positive infinity, we have to know how function behaves at the end behavior. Limit as x goes to positive infinity of the exponential function a to the x, with a being greater than 1. For example, I can say 2 to the x. Okay? We can nicely see as x getting bigger and bigger, 2 to the x is also getting bigger, and function is going up, function is increasing, and it's actually increasing really fast. That means this is infinity. As x goes to negative infinity, the same function, we notice based on the graph that the whole function a to the x is approaching 0. Okay, now looking at the exponential function with base less than 1, for example, 1/2 to the x, it's just the mirror image with respect to the y-axis. As x goes to positive infinity, a to the x, 1/2 to the huge number, it's approaching 0, because we will have 1/2, 1/4, 1/8, 1/16. Since denominator is getting bigger, the whole value is getting smaller. And opposite, when x approaches negative infinity, values will flip. Yeah, this means that value will be extremely big, positive infinity. Okay, that means knowing the shape of the exponential function, we can compute some limits. We also remember natural exponential function is the function with the base e. E is the number definitely greater than 1, I think approximately 2.71, which means that's the shape. And looking at the end behavior, as x goes to positive infinity, e to the x also goes to positive infinity. The function is approaching huge numbers. As x goes to negative infinity, the graph of the function is approaching x-axis, and this is value 0. Okay, and of course the exponential function is the most frequently used occurring function in calculus, and has lots of application in nature. Okay, so now let's just try to, let's compute a few limits with the compound function. Limit of the function e to the power of 1/x as x goes to positive infinity. As we can definitely see, we have inner function and outer function. We have a composition of two functions. And since function e, exponential function, is continuous function, then I can only focus on that limit of the exponent. Okay? That means limit how 1/x behaves as x goes to positive infinity. Okay? And as x goes to positive infinity, 1 over x goes to 0, of course. I can draw this function, okay? And function 1 over x is just hyperbola in the first and the third quadrant, and we can nicely see limit as x goes to infinity, 1 over x goes to 0. Because we can think this way, 1 over big number, it's always small number. Okay, I can even say 1 over big is simply small. Okay, and I can say this way, that means this limit is 0, e to the 0 is 1. Or, I mean, I can leave it, we can leave it this way. Maybe the next exercise I will solve a little bit different using like an additional label, additional variable. Okay, but we can see what I did. The first thing that I did, I focused on the inner function, and then I applied the outer function, which was our new e, the exponential function, the natural exponential function. Okay, exercise number 2. E to the power of negative x squared as x goes to negative infinity. How this behaves. So what I can actually do, I can name my inner quantity t. Maybe we will like this way. And then I will focus on the limit as e, I mean of the function e to the power of t, as t is approaching, and we don't know what t does. But t is defined as a limit as x goes to negative infinity of negative x squared. And we can think, we can draw it, maybe that's the easiest way, xy plane, function negative x squared, this is positive x squared, right? Okay, but negative x squared is just flipped. I mean, this is function negative x squared. And as x goes to negative infinity, we will square that negative big values, but we still have negative in front. That means this limit is negative infinity, and we can see on the graph. Function goes to negative infinity as x is approaching negative infinity. Okay, that means now I have my answer. T actually goes to negative infinity. And now how e to the t behaves at negative infinity, that's our new function. I mean, we knew, we're just investigating. This is e to the t, and as x goes to negative infinity, the whole function is approaching 0. Yes, you may like the t notation. Okay, the same thing. Limit as x goes to as x goes to 2 from the left-hand side, how function e to the power of 3 over 2 minus x behaves. I will do the same thing. I will investigate this exponent, which I will name t. And at the end, I will evaluate limit of e to the power of t. And t does, we don't know what. T is simply a limit as x goes to 2 from the left-hand side of the expression 3 over 2 minus x. Okay, that means what I have. Direct substitution is telling me that if I substitute 2 in the denominator, 2 minus 2 is 0. A number over small number is a big number. Oh, so we know that. However, I have to check the sign, plus or minus, because it's extremely important. 2 ends of the number line, yeah? And 2 different behaviors, which means I have to check if this 0 is from the left or from the right-hand side. Because we know I did put 0, but this is theoretically not really 0, it's just a small number. Because that x is not really 2, it's 2 from the left which is like, for example, 1.9. And when I take 2 minus 1.9, I'm actually getting positive number, tiny number positive. It means this is positive, and consequently, infinity will be also positive infinity. That means t goes to positive infinity. We don't have to write plus, but I'm just trying to be more pronounced. Okay, and e to the power of t, our natural exponential function, actually that's supposed to be t, as t goes to positive infinity, function is also going to the positive infinity. That's e to the t. Okay, positive infinity, that's the final answer. Okay, and let's look at this one. Limit as x goes to infinity, e to the power of x squared minus 5 over 10 minus x squared. The same thing. Limit of e to the power of t, I will name the whole exponent t, as t goes, and we don't know. T is simply a limit at infinity of the rational function x squared minus 5, 10 minus x squared in the denominator. And when we have rational function, limits at infinity, we can easily compute this way that we can look at the degree of the polynomials from the numerator and denominator. If the degree is the same, x squared, that means the degree is the same, then we have to take the ratio of the leading coefficients, which is 1x squared and negative 1. 1 over negative 1, of course, is negative 1. Okay, that means t goes to negative 1. It's not really the end of the domain, but still a nice answer, 1 over e. And limit at infinity of the exponential function 1.01 to the power of x. That means we know right away that is infinity. That means this question is just testing if we remember the shape of the exponential function with the base greater than 1. Even if it's just greater a little bit, it's still that behavior. And this is 1. Oh, nice one, challenge. Limit as x goes to pi over 2 from the right-hand side, 3 to the power of tangent of x. Okay, I mean it's exponential function, it's 3 to the power of tangent. And I will name this t. Limit as limit of 3 to the power of t as t goes, and we don't know what t is approaching. Let's check. T is a limit, that is the behavior of the tangent of x as x is approaching pi over 2 from the right-hand side. And drawing a tangent function, we will see an asymptote at negative pi over 2, positive pi over 2, 3 pi over 2, and so on. Okay? And tangent is just looks like that. Okay, really nice, because tangent of x could be defined as a sine of x over cosine of x, and cosine of x, or maybe cosine at pi over 2, is 0. That means tangent is not defined at pi over 2. Okay? Tangent is not defined at pi over 2. Okay, but we can see the behavior at pi over 2 from the right-hand side. Function tangent goes down, not plus, negative infinity. That means this limit is negative infinity, and this is our t, negative infinity. 3 to the power of t, this is my new function, and this is also the same shape. It's exponential function with the base greater than 1. That means 3 to the power of t at negative infinity. I can draw a little bit better. It's 0. It's simply 0. And that means this is really nice limit, combining trigonometric and exponential. Okay, that means I believe we know the shape of the exponential function. Then we know consequently the limits. Now let's look at the derivatives. Okay, that's the second part of this session. Okay, we will start with the definition of the derivative. Okay, that we will take the general exponential function a to the x, and the only tool that we have is just the limit definition. Okay? Beautiful definition. Limit as h goes to 0, f of x plus h minus f of x over h. Okay, I will take this limit and I will evaluate for my function. That means f of x plus h, it's simply a to the power of x plus h. F of x is just a to the x all over h. Okay, and I have to compute this limit. One of the first step that I will do, I will expand a to the power of x plus h. Okay, that means when we have a to the power of x plus h, I can rewrite this. Oh, hang on, why? Oh, okay. I think I'm missing one step. I can write it up. I will say is a to the power of x times a to the power of h. Because when we multiply the same base, we can add the exponents. Okay, now it's here. And we can see a to the x is common factor. Okay, and I will factor out this. And with respect to the limit, because limit is only telling me the information about the h, with respect to that, a to the x is a constant, which I can put the constant outside the limit. It's simply a constant. Doesn't depend on h, it's just the constant. Which means we have to focus on this limit. Yeah? If we will look closer, this limit is really interesting because this limit looks almost the same like this one, correct? But we have, what's the difference? Let's see, a to the h plus x. And this one is 1, which looks like a to the 0. That means the red box is the same like blue box with x being 0. Yeah? And again, the blue box is simply the derivative of the function a to the x. That's when we do have some interesting things. Of course, I can just ensure you don't have to know all of these steps. You have to just know the final thing, which means the formula for the derivative of the exponential function. But I'm trying nicely to derive for you to see where the formula comes from. Okay, that means the red box is definitely something like this. I can use my red pen back. Derivative of the function a to the x at 0. Okay, I can maybe remove a few things. That means I have my a to the x, and the box, as I said, is simply the derivative. Yeah? That means the limit is the value of the derivative. This limit is the value of the derivative of the function a to the x at 0. Makes sense, looks the same. And that means it's an interesting situation. The derivative of exponential function, first of all, is proportional to itself, because the formula, this is the formula, is still not finished. But so far, we have this formula, which means what's the derivative of a to the x? Is a to the x times derivative at 0, which we still don't know. We will compute this limit. Okay, we will compute. Okay, that means it's interesting situation. Okay, let's keep working. Okay, that means now we definitely know that this limit is the derivative at 0, because it makes sense. When I add 0 and when I say a to the 0, it's definitely 0. And we will try to evaluate. The only thing that I have for now, I have just the numerical proof, okay? I will take two functions, like instead of a, I will put 2 to the x, and I will take 3 to the x, just to see what's happened. That means taking function 2 to the x and 3 to the x, this is that's the limit, that's the above limit. And if evaluating with respect to h, we know that h goes to 0. H is almost 0, but almost 0 means that the values are getting closer to 0. 0.1, 0.01, 0.001, 0.0001. And then computing these two limits, we're getting these numbers, which probably they're not telling us much. The only, like, when I would like to analyze them, I will say this is less than 1, this is greater than 1. Okay? But I can tell you, yeah, this number, it's tend to be natural log of 2, and this one, you can probably guess, natural log of 3. Okay, that means it's really related to the base. And actually, that's how it works. That means what I can say. I can say that value of this derivative at 0 will be simply ln of a. Okay, and we can come back. This is the same thing that I had on my original slide. And now we can say that this limit, which we just proved numerically, is just derivative, but of course is ln of a. Derivative at 0 of the exponential function is ln of a. ln of the base a. And of course, that's the full formula. No? That means I can say derivative with respect to x of the exponential function a to the x, that's a to the x, its function itself times natural log of the base. This is the formula that we have to remember. And that's it. Okay, that's the only thing that you have to remember is the formula. We will still practice, of course. But I have one thing just to show you. Looking at this, again, the same values. We know that this is natural log of 2, this is the natural log of 3. And this one, as I said, is less than 1. This value is greater than 1. But what we want, mathematicians, they said, oh, will be really nice if we will have exactly 1. Okay? We want that value to be exactly 1. Which means this corresponds to the function 2 to the x. This corresponds to the function 3 to the x. Okay, that means now the question is, thinking about this limit, okay, and knowing that this limit is ln of that quantity, okay, that means mathematicians, they wanted to have natural log of what number will give me 1, exactly 1. And of course, that's one of the ways to define a number e. I know that you probably watching this, you saying aloud, that's the number e. Natural log of e is 1. That means we can see that's how, one of the way to define, to look at the number e is actually through this limit. This limit will give me 1, which I can say ln of e, which of course is 1. Okay, then I can okay, let's wait a little bit. Then we have a little bit of And just a little bit of explanations. Having functions, we can see 2 to the x, 3 to the x, and e will be between, because the number e must be between 2 and 3. We know why. And it ended up being 2.71. Okay. And the exponential function e to the x has the property that it's its own derivative, because when we will use the e to the x, what is the derivative with respect to x? We can follow the formula. It's exponential function. That means I will copy the same function, e to the x, and follow the formula for the general exponential function. I will have ln of the base. But ln of the base is, of course, 1. That means e to the x derivative is just e to the x. Yeah, very nice. And the geometrical significance of this fact is that the slope of the tangent line to the curve e to the x is equal actually to the y coordinates of that point, which is 1. Yeah, because will be simply the value of the function at 1. Yeah, itself is just the same function, because slope is derivative at 0, and of course we know that is 1. That's what we wanted. Okay, this means I do have that formula. Derivative of e to the x is e to the x. When we have to combine with the chain rule, e to the u is just e to the u and times u prime. Okay? The same for the exponential, for the general exponential. A to the u, it will be a to the u times natural log of a and times u prime. Okay? Okay, that we do have all of the formulas, and let's just practice. Differentiate e to the power of tangent of x. Derivative of e to the tangent of x is the same function, e to the tangent of x, times derivative of tangent of x. And I know that you're saying aloud, derivative of tangent of x is secant square of x. That's it. Exercise number 2. Square root of e to the power of 5x. I can use 2 different ways, but let's keep it this way. Yeah? First of all, I will differentiate square root. Derivative of the square root of x is just 1 over 2 square root of x. You can practice the power rule. We did this in section 2.3, I believe. Okay, that's me. And you probably remember me saying, remember that derivative. Okay, that means derivative again of the square root of x, it's 1 over 2 identical square root of x. Let's see. Derivative of the square root of x, it's 1 over 2 square root of x identical. Okay, I have to copy the same function, times derivative of that inner function, yeah? Times derivative of that guy. 1 over 2 square root of, and derivative of e to the power of 5x is e to the power of 5x times derivative of 5x, it's 5. Okay. We can definitely simplify using the algebra. I can put 5 and e to the power of 5x to e to the power of 5x. And actually square root means that we're taking everything to the power of half. 5 over 2 e to the power of 5x, e to the power of 5x over 2. I'm just trying to use the algebra. When we have the same base and we're dividing the numbers, we can subtract the exponents. 5x minus 5x over 2, we will get this, and we will get 5 over 2, because this is 5 and this is 2.5. And I can rewrite again 5x and half, and I can rewrite e to the 5x and the square root. Okay, just a little bit of algebra, but I believe this my second line is the most important because we see nicely chain rule and the new formula. Differentiate 2 to the power of x squared minus 1. It means derivative of the exponential function 2 to the power of x squared minus 1 is the same function 2 to the power of x squared minus 1 times natural log of 2 of the base and times derivative of the exponent. Chain rule. Yeah, that's my chain rule. I can copy this, natural log of 2, and this is just 2x. And let's leave it because we can nicely see all of the parts. This is, of course, part of the formula. And oh, that's even more complicated. 2 to the power of 3 to the power of x squared. It means derivative of the exponential function 2 to the power of this is 2 to the power of the same thing times natural log of 2 and times derivative of that exponent, because this is my exponent. Okay, I will copy this part because it's always the same function. This is part of the formula. And now another exponential function. Derivative of 3 to the power of x squared. It's 3 to the power of x squared times ln of 3 and times derivative of x squared, to which I can just put 2x. Again, we can nicely see two parts. I mean, we can see all of the parts. We use the chain rule twice, but ln of 2, ln of 3, part of the new formula for us. And that's all of my exercise for this session. This is the summary of the formulas. Again, derivative of the exponential function is the same function times natural log of a of the base. Or if the natural log of the base is 1, we can skip it. Derivative of e to the x is just e to the x. And I type for you the chain rule. Derivative of a to the power of u is a to the power of u, ln of a, and derivative of u. I just use different notation. Yeah, the Leibniz notation, du dx, but this means the same, u prime.